As you can see from the title, this is a very exciting modern title for a very old problem. So this is a TMLS, nice title to say data cleaning, which is a lot more boring than this. So today I'm going to tell you about this problem. We spent a lot of time working on this problem since 2009 or so. We tried everything that worked and didn't work, mostly didn't work, till 2016 or 2017, where a lot of support from machine learning community helped people like us working from kind of the logic aspect of the problem to think about this problem as an inference problem, and started to highlight some interesting challenges that was both for database people and data science people, but also for machine learning people as well. So today I'm going to tell you about not Tamer and not other things. I'm going to tell you about HoloClean. HoloClean started as an open source project in 2017, and we're now in the process of commercializing it. You're going to see the first ever inductive t-shirts tomorrow in the expo, where the 4 teams are going to be here to demo the commercial version of HoloClean. So with that, let me tell you what exactly the problem that we're trying to solve. If you are an enterprise or closer to the enterprise work, this talk is mainly about structured data, so there will be no images or like more exciting stuff. It's going to be all tables and boring tables. But there's a lot of figures behind it for the machine learning models that we're going to build. So if you're exposed to that community, you know that there is a big investment near what we call the ingest box, where people just get a lot of data all the time, either put it on Iron or put it in their cloud or private cloud and all of these fancy stuff. And on the other end of the spectrum, there are the interesting people that creating all the pretty pictures and putting these in Tableaus and other machine learning and analytics platform to get insights, market research reports, and sell them. Everything in between is done manually, and people spend a lot of time trying to fiddle with these data. I have an intern student in Waterloo that spent actually 3 months in Toronto in a machine learning company, and I asked her what did she do, and she said Excel sheets, because that's exactly what she's doing 3 months, cleaning data and labeling data for the real scientists to use it in their models. So she was a lot disappointed with this fact, but she was not alone. So because of this fact, there's a lot of kind of big industry happening in between. Some of the companies that you see here are older company, more established, SAP and Informatica, but there are also newer company in the last 6-7 years, Tamer, Trifacta, and others. And they're all trying to solve that space, how to automate data prep, either integration, deduplication, record linkage, classification, schema mapping, and so on. Still, a big problem is data cleaning itself. And while it looks a lot easier than something like data integration, because you have like tons of sources and it's a combinatorial problem, it turns out that just for one table, to be able to look at any cell and say, this cell looks fishy, it didn't come from the same distribution, or what is the most probable value that can go in that cell and become a legitimate value is an actually very hard problem. And it suffers from massive sparsity and massive challenges. So there is a kind of impedance mismatch between our ability to provision really complex models and optimize the hell out of these models. We have like tools, Overton, Ludwig, and that's even higher level tools than PyTorch and TensorFlow. But still, for data cleaning, we have Excel and some Python scripts. It's really embarrassing. And the labor-intensive aspect of it, it's not only daunting for engineers, it's also costly. There's a lot of people spending valuable time, and I always make this joke that data scientists in big enterprises are the most overpaid janitors of the world, because their time should be spent optimizing models, coming up with model selection, pushing the frontier of AutoML, but instead they're labeling cells and doing JSON to CSV and vice versa. So here is a good-looking table that, as I say, looks like a table and smells like a table, so it must be a table. But it's actually full of garbage. It has duplicates. It has syntactic errors. So if you're doing aggregates on New York, you'll get it wrong. It has missing values. And these missing values are not applicable. They're actually missing. It just happened that we forgot to put them, or the extractor didn't put it in place. And we know that this is a massive impediment to downstream applications. And you can talk all what you want about robust machine learning at the end. But for the enterprise, for structured data, robustness is not something that we experienced. Very few errors can screw up all your analytics completely because you're not looking at problems that have a lot of redundancy. You have a problem, you're looking at problems in which everything appears once or twice and sometimes less. And harder to find or harder to spot problems, what we call integrity constraint violations. These are violations that of your business rules, for example. In this case, it's what we call a functional dependency if you take a database course. And it basically says if you agree on zip, you should agree on city. You can think about a lot of other things, like more complicated things like denial constraints, in which if two employees, they are in the same role, the manager should make more than the employee, and so on. All of these business rules can be encoded efficiently, but you might find violations of these rules, and it's hard to spot because you need a query to be able to get it. So data cleaning or data prep is taking this table into a good-looking table where duplicates do not exist, and these clusters are now mushed together and replaced by what we call a golden record. Missing values are imputed if you can. So if there is enough signal in the data to recover that missing label, why don't you do it instead of asking a human? Or at the same time, or like if you can't, at least identify that it's not a recoverable label and I need to ask somebody. Syntactic errors and so on. So this is what I call data cleaning. This is a very old screenshot from when I was a PhD student, which is like a long, long time ago, when some of these techniques, one of these websites occur. And if you take a database course, we lied to you and we said there exists something called nulls and you should worry about it. And it's great for passing the exam for database course, but in reality, there is no nulls. I wish there were. I wish somebody tell you it's a null. Oftentimes, we have this 999777 -- question mark, ask Mary later, which all means null. I do not know. And very few times you say it's not applicable or sparse. So the problem is how we take signals like integrity constraints, the statistical signals in the data, put all of these signals together and come up with an inference engine for structured data in which data prep, data cleaning, and all of these problems is just one task, running the model on the structured data. Machine learning comes to the rescue. It's a very interesting vehicle because it's a principal backend. I can actually trust what I'm getting. I can melt all of these things into one melting pot and start getting, I have mechanisms. I can talk about priors. I can talk about posterior. I can talk about things. The problem will be you will never have enough training data to build these interesting models, and I'm going to show you that in a while. You will have an Excel sheet. A friend of mine just showed me an Excel sheet yesterday, which is just listings of things, and it has 16,000 columns, 40,000 entry. You know what that means? It's a universe with 16,000 dimensions and 40,000 stars. Can you see anything? Probably no. It's going to be black and empty. So you cannot really learn anything from this if you just assume that these are independent data points. So I need all of your domain knowledge to I need to unveil the structure in the data to be able to learn anything, if at all, something useful. So I need to represent all of these data and these signals in one melting pot. I'd like to be able to inject domain knowledge and constraints explicitly in these models and do not depend on the network to reveal it or to mine it back. And I need to have it at scale. Scale will become very evident once I show you what is the most straightforward way to deal with structured data. So in 2016, or beginning of 2017, we started this project. There's a bunch of papers here. It's not for bragging, it's just to give you titles and to show that there's a lot of collaborators on these. So go and check it out from my website or from the HoloClean website. And we started to think about the problem, how we think about data cleaning, this very old problem, in a probabilistic way in which inference becomes your engine. And let's work on the technical and engineering challenges to go there. So to start, here is our view of the world, why data cleaning is actually a machine learning problem. I'm going to make some assumptions now. I'm going to assume that the data god will generate data clean and nice, some data that we all like. And then the polluter, or the devil, will mess with this data in a channel. And then what you see is the data devil's work. So you'll see a very messy data at the end, which we call J star here, which is basically went through a noisy channel. Now, if I think about if the word is as simple as this, then if I can parameterize the generative process I, and I can parameterize the pollution process R, and I try to estimate these parameters from what I'm observing, if I can do that, then I can model many, many of these tasks as inference tasks. For example, data repair becomes the most probable clean world that resulted in this J star. Data detection or error detection becomes the probability that the polluter messed with this particular cell. So I can actually ask these questions in a very kind of uniform way. Of course, the problem is, what is that model? You need to choose the parameterized model and you have to live with these choices and make it work. So in 2017, we had a very kind of conceptual way of modeling that problem. So I don't have to introduce to this crowd, but basically think about it as just massive factor graphs in which every cell in the database is just a random variable. And how these random variables operate with each other or interact with each other is described using the factors. Okay? So if you don't remember what factor graphs are, it's just a graphical model to represent how data is correlated. And it's an undirected one. Why we like these things? Database people like this so much because it has one-to-one correspondence to our constraints and so on. So it's kind of like we love MLNs. Nobody else in the machine learning community love MLNs, but database people love MLNs because very close to us in terms of modeling data constraint. So here is what we're going to do. Imagine these 4 cells, the first tuple and the fourth tuple, city and zip give you 4 cells. Chicago and 60608, Chicago and 60608, represented as these 4 cells. And I'm going to start modeling all my signals as factors. One signal, for example, will tell you co-occurrence is kind of important. So when I'm trying to figure out the city, I'm going to trust the address somehow, and I'm going to tell you a city that co-occurred in your database with that particular address should get a brownie point. A city that never co-occurred with that address will not get that brownie point. So now I'm starting, as I'm adding factors, not everything is equiprobable anymore, and I start to have words that are more probable than other words. The good thing about this, I can inject more and more knowledge. For example, I can add explicit structure in that space that says that these 4 cells depend on each other. So a functional dependency for me is just a 4-way factor that tell you when I choose the zip and the city, if you choose these 2 zip to be the same, you better choose these 2 cities are the same. And if that happens, you're going to get a good brownie point. If you don't happen, I'm going to get you a slap. And you keep accumulating these brownie points and slaps, and then you start to get a probability distribution on every cell, if you like, and even you can get kind of run map inference or something like that at the end. That was great and dandy. We liked it. We solved the problem. We model it. We just have to put it and learn the parameters of these, learn the weights, and we're done. Just, why it's hard. Few problems appear. We never have enough training data clean enough to learn these weights. The number of factors are ridiculously more than what we can even try to model. So that doesn't work. It's a good way of thinking about the problem, but it doesn't work. So we started to inject some of our database knowledge. And in databases and data cleaning, people are fond of something called minimality of repair. And the idea of minimality of repair is if you are going to guess what the right values are for your data, why don't you stay close to your local observation? So I'm going to prefer an algorithm that will choose less changes than another algorithm if you can get conforming with the rules. So because I would like to prevent you from deleting everything and you say, here, it's clean, nice and clean and empty. So I would like to say, well, I would like you to be minimal. I would like it to be actually close. And we said, can we translate that, and instead of finding the global optimal for these parameters, can we find local optimals around the current observations of the data and see if that can help us? It actually helped us both ways. So here's what I'm going to do. I'm going to butcher that factor, and instead of 4-way factor, I'm going to make it 4 factors. Each one of those is just univariate. And in this case, each factor tells you, when you figure out your value, you should play nice with the other observed values of the other random variables, the current initial value. And you should shout at me and says, like, that's not the same thing, and that's probably not, like, you can get inconsistent results at the end. I said, yeah, I know. We're going to have lots of these, and we're going to hope that they're going to work together well, and finding local solutions just next to the current observation that make most of these things just work. And that's exactly what happened. Why I'm telling you this? Because that's our leap of people, how to think about the problem from kind of logical perspective, put it into graphical model, thinking about it probabilistically, and starting to work towards, can I get efficient models for this to work at scale? When we started this work, our baseline was on green plum, and it took 24 hours on 16,000 machine for 1,000 tuple. Just to show that it's not, you shouldn't do it that way. And the current state of that implementation is 10 million record in 2 hours on my laptop. So it's getting there. It's now starting to be usable. So let me tell you, so what other techniques we do. We do things like, like lifted MLN or templated MLN when we start to tie the weights and start to say, I'm not interested in learning just all these factors. I'm learning kind of the importance of the DCs or the function dependencies and what have you. And we started to add more and more structure and domain knowledge in the problem with the hope that it becomes a lot smaller model and a lot more learnable. And then we throw all of this out, and we started to have, as you guessed, a little bit more efficient, modern implementation of these based on a bunch of concepts that work very well for us. So in SysML, very soon, hopefully you're going to see a paper, we call it the AIMNet backend, that talks about how to use very simple attention mechanism that allowing to encode the context of every cell given everybody else. And then this attention mechanism will choose what's the most important kind of parts of your context that kind of contribute in predicting you. And that's allow us to get all the statistical property in kind of an auto-encoding style, but also append to it all the denial constraints and violations and function dependency and business logic into this massive feature that I can then shove to my predictions, and I can get like a nice, simple and very explicit fusion between the statistical properties of the data and the business rules and what they vote on. So you don't have to think about rules anymore. And some of our customers love this because they take their rules, they shove it in as either labeling functions like Snorkel style, or as just part of features that we will learn the weights and the importance of these rules. So you don't have to write rule-based systems anymore, which they hate, because maintaining these rule-based systems is more problematic. This system is also completely self-supervised, if you like, sometimes weakly supervised using the rules that I told you about. And the idea is, is to learn from ourselves. There is a lot of information in data, so we mask some of the input, we try to get it back, we iterate till we find a model that kind of model the joint probability distribution of all of these cells, accurate enough to be able to use it for prediction. We do a lot of tricks also for distributing it, slicing it, building different models for different slices, and all the tricks that if you kind of deal in that domain, you probably went through it one way or another. I'm going to dig deep one of these contributions that we did for an instantiation of the problem for detection, in which we went directly after the pollution model. And just to highlight some of the problems that working with structured data kind of you will face. So here, this is a complex model, but it's not very strange model. You will come up with this model as well. So I built a model that will be able to classify if this is wrong or not. Okay, so I'm going to get a cell, and I build features that has to do with co-occurrence with other things, language model that describe how the cell is actually working. You can do whatever you want. And this model will be not that complicated, and it will be very expressive. And this model is probably capable of telling you for every cell if it's correct or not. It's just a single classification task. What is the biggest problem in this interesting yet straightforward model? What do you think the biggest problem is? I'm going to use this for error detection. So I want to train a model that tells you errors from not errors in a specific data set. So you feel free to overfit the hell out of this on your table. I don't want this to work for any table. I want it to work for your table. So the first thing that you need is probably to train that model, right? That's a discriminative model. I need to train it. I need to show you a lot of examples of errors and a lot of examples of good citizens, so you can tell me this is a good citizen, this is not a great citizen. The problem in error detection, if you work with enterprise data, that the errors are extremely small in number and extremely heterogeneous in types. And that basically means in order to train the model, you need to probably find all the errors, and then you can train the model to find them back. That's not a great way to land the customer, by the way. That's not how the interaction works. So we face this problem. By the way, active learning and all of these things, I can go through details, will not work in these kind of things. This massively imbalanced classification task are notorious for many of you, and you went through it before. So what we did is an interesting one that we've published in Sigmod last year. And we started to say, well, if we are thinking that the data devil exists, why don't we build a different model that is a lot easier? That model will generate errors. It will just fake as many errors as possible. And I can inject all my domain knowledge in that generative process, and with few shots, I can probably customize it to my data set. And the job of that model will be just generate what if this particular clean cell was a bad cell. And I'm going to simulate the actions of the devil on my clean data, and I'm going to generate as many bad examples as possible. We have to be careful not to take these bad examples, put it back in the data, because you're going to screw up the distribution. But we're going to do this what-if featureization of these errors to teach the model that if the devil played with this cell, it will look like this, or it might look like that. And I kept doing that. And that's how we taught this model to discriminate. So it's a generative model that will generate the error example, simulated featureization for the discriminative model, and now you have your model trained. This is an example transformation, for example, in which we found typos, and we learned from all the typos. You give me a few examples, and I don't want to learn how to identify typos. I would like just to learn a machine or an automata or a transformation that simulate legal typos so you don't make up stuff. And by that, you start to generate all of these kind of cell value representation of these errors. You learn that model, and then the classification task is that easy. Is it correct or is it not correct? Why I'm telling you this? Because it's one of these challenges that you will have when predicting structured data. You're just not having enough training data. So you have to be innovative on either generating your own, learning from noisy data, and if you talk to anybody that would like to use this in production, they will not use any supervised model. This is a typical pipeline. Like, if you are also in the data prep or data science, people think in terms of pipelines because they build this massive data science platform, and they realize that one size doesn't fit all, and you cannot have one monolithic system that solve all your problems. So they start to have ingest box followed by kind of an integration box followed by transformation box, clean and repeat and so on. And they stitch these Lego pieces together. And as the community and the industry is kind of maturing, they need to start to choose best in breed in each of these boxes. And this is how people do bottom-up kind of building of their backend. This is a typical pipeline. It's not the only pipeline in which data comes in with few shots. As I told you, we just find the errors. We separate the data into non-trustworthy and trustworthy. We take the trustworthy data. We train a different model that I didn't tell you about today, but it's going to be on SysML soon, that basically implement the graphical model that I told you about to be able to impute and give you marginals on every cell. And in this case, you can now shove it back to downstream application that just run map inference, for example, to give you the most kind of probable value. Or for when it's very high entropy at the end, you can shove it to your QA, and now your data scientists have to look at 5% of the data, not staring at millions of records unnecessarily. I want to tell you about 2 use cases very quickly about these things. By the way, I'm around if you'd like to ask about the details. I just didn't think that it's useful to go through the algorithm of these things. But the papers are there, and the demo is going to be tomorrow in the fair under inductive I'm going to tell you about. But let me highlight 2 use cases that kind of created a difference in some of our early adopters. This is a market research company, and what they do is they take kind of entry from their providers, transactional entries, and they categorize it with certain SKUs. And they want it to be as accurate as possible because they aggregate and put it in their OLAP at the end, or warehousing, generate a report, get paid for that report. So labeling and categorization for them is everything. So they give us 6 months worth of labeling, where they kind of label one at a time, and they have their own Elasticsearch systems and so on to make the labeling as fast as possible, but still their scientists need to label things. And they give us this back, and we said, why don't we give us only 2 million record, and we're going to try to see if the 60 million record left in your 6 months is actually recoverable without any more humans. So just give us this 2 million, and I'm going to build a model. And as you notice, it's not cleaning anymore. It's just pure categorization. But I'm going to assume that the 2 million record in the training has values, and everybody else has a missing value. And we just run imputation on it, and we recover 97% accuracy, all the labels. There is just enough redundancy in the data in 12 hours, by the way. So we learned 10 hours on my laptop on 2 million record, and then we ran on the 60 million and 2 million, and we got 97%. They got greedy and started saying, why 3%? why you're different from our ground truth. So we opened that 3% difference, and 70% of the cases, the ground truth was wrong. And again, that's not repeatable. I'm not going to imagine that this is happening with every customer, but it tells you sometimes that labeling, human labeling, is actually not that great because the machine have way bigger context than these humans. Another interesting use case with a big insurance company in the States, and they buy these massive data sets, and if it has some errors, then their analytics is kind of suboptimal, and this is how they sell policies to people and premiums and so on. And one of the most important, I mean, it was a surprise for me, one of the most important columns for them is zip code, because this is how they categorize people and put them in the right zip code and so on. And it turns out that this data is extremely hard to eyeball with your naked eye, because errors in zip code are actually oftentimes at the boundaries of areas. So you need to kind of highlight it with something else and map it and look at it and put it on a map and say, oh, it's actually in the wrong one. And the tool kind of generated all of these reports and recovered 90% of these errors without any human interaction, without a single label from them, just learning from the data. So they're extremely happy. So anyways, my hope today that I intrigued you about that this problem called data cleaning, which used to be extremely boring, is now a very interesting structural prediction problem that requires techniques in scalability, modeling, training data generation, learning from noisy data, and it has like 2 or 3 of my PhD students are actually pure machine learning students who are interested in solving these hard problems. So it's a gold mine, and if we solve this, then classical problems that we kept handling it in a piecemeal way, like error detection, anomaly detection, outlier detection on numerical data, outlier detection on categorical data, they're all the same beast and have to be dealt with the same back engine. And that's a great opportunity to automate that ugly piece in the pipeline so people don't spend enough time, they spend enough time doing more interesting stuff. As I told you, tomorrow you're going to see some 4 people, hopefully they're going to show up tomorrow. They are building Inductive with me and a collaborator of mine in University of Wisconsin-Madison. And these 4 they're all Waterloo based, but they're going to be in black t-shirt with that logo on it. So ask them about commercialization of HoloClean. They're probably going to have demos as well for you tomorrow. So if you're staying away for the fair, go and hang out with these guys. Thank you so much for listening. Question? I'm sure we have, I think, a few
thank
questions.
you very much for the talk. We have time for 1 or 2 questions. And there's a mic in the middle of the room if anybody wants to go there, or I can just hand it. Yeah.
Thank you for a great talk.
Thanks.
You mentioned about the factor functions as one of the methods.
Yep.
What other methods have you tried and not succeeded? Because that would be great.
So let me reiterate very quickly that these, thinking about the problem as a PGM problem and factors and so on, it's more for modeling. Actually, we don't do any factor graph inference or anything like that underneath. The actual implementation is just deep learning with attention layers. But we know that these features came or kind of to some approximation representing these factors and features. So we'd like to we started by thinking about the problem this way, but to get kind of fast and plausible implementation, we had a lot of kind of modern new ML principles at our disposal, so we didn't do any factor function or anything like that. So it's purely modeling exercise.
Any other questions?
One.
Oh yeah, go ahead. It's not on?
I don't think it is.
I think it is.
Okay, all right. So thank you, Professor. This was very intriguing. So I've been in enterprise software my 13 years of experience. So I'm one of the janitors that you talked about. So in terms of, I think, scaling the solutions that you talked to us about here into the more complex problems that we see in enterprise. So for example, to give some examples, in POS data, for example, you have retailers who do returns in a very funny way, and that's very hard to clean. And you have companies that have grown through mergers and acquisitions, and they have accumulation of data that has been stored in different ways. So how do you think the solutions that you talk to us about here are going to scale to solve these types of problems?
So if I can rephrase the question, how to make sure that these kind of interesting and nice way of modeling the problem work on real good, like real looking data that doesn't look like this nice table that I showed you. And what we're focusing on right now is to actually completely agnostic to the verticals, and like our interaction with the business is just these priors that they express as business rules. We take that and we just push in the system as soft features, if you like, and we don't care about anything else. So our approach for scalability is being agnostic to the semantics. So we're not building a solution for pharma and a solution for this. If it's structure and it looks like a matrix like this, then we whack it with whatever we have. And we have a bunch of interesting things that I might be show you tomorrow, like structure profiling the data, getting like a very quick Markov blanket, if you like, so I can have very small models for every target column. And we do a lot of these tricks. So far, we're scaling very well on real data sets. But yes, there are lots of tricks that you need to be cognitive of to be able to do it at scale. I can talk to you more.
Okay, great. Thank you.
Any other questions?
We have time for one more question.
Maybe there.
I saw you first. Do you want to just stand at the mic?
Thank you so much. It was really intriguing and interesting. So problems like data deduplication or duplicate rows or multiple values for the same integrity across multiple tables. Did you address these things?
Right. So I have another company on it called Tamer. So Tamer does only deduplication schema mapping. It's 120 people, $70 million in funding for 7 years, just to deduplicate things. So and they're not stupid, so they are very smart. So it's a very different problem. Dedupe and integration is a combinatorial problem, so it's an n-square problem. But the ML task is actually trivial. It's classification. These are linear in the input size. They're only n. But the machine learning task is quite complex because I need to model the whole context. So they are very different in nature from engineering and ML.
So it's not included in this. Not included in this scope. Okay. Yeah. Thanks.
So thank you again, Ihab. Very interesting talk,
Thank you,
especially
guys.
for data scientists. Thank you.